So what we're going to look at in this video is how air resistance affects our motion relationships. Now, air resistance is a force, and what the air resistance does is slow down an object that is moving through any liquid, any fluid. Now, when we're considering motion, we're more likely to come across air resistance when we're considering an object that's falling or flying horizontally and vertically through the air like a projectile. It's assumed that all objects fall with the same acceleration. In reality, an object falls with some degree of air resistance. Some objects encounter more air resistance than others. Now, we will talk about the physics of air resistance in the next chapter when we talk about forces. But what we're going to look at now is we're going to see if we do have air resistance, how does this acceleration change? How is it different? Well, one of the phenomena that you might have come across before is this idea of terminal velocity, which is a consequence of air resistance as an object is falling through the air. As an object falls through the air, it accelerates due to gravity, right? So the velocity increases. As the velocity increases, the opposing forces of air resistance increase. So what you find is that this air resistance starts to build up. So what you end up having is a counter force to this weight down. Eventually what happens is that the object no longer accelerates, and this is what we call terminal velocity. Now, this is footage of Felix Baumgartner, who is probably, I think it's still the record for the highest sky jump. Basically, he jumped from the edge of the atmosphere. I'm going to see if I can start it and we can look through that video. And basically, he's there he is, just basically on the edge of his tiny vessel. I can just about see you can see the curvature of the Earth. That's how high up he is, 128,000 feet above the ground. And eventually, we'll speed it up a little bit. You'll be able to see as he starts flying through the air. There he is. He's about to take a leap. It's a bit nerve-wracking, this bit, isn't it? There he is, about to jump on his marks. Come on, you can do it. And off he goes. So let's have a look at air resistance in action. So there he is, plummeting to the earth. And you can see he's in free fall. So you can see this clock ticking away as he lands. Now, what eventually will happen to Mr. Baumgartner is that eventually his air resistance, the air resistance acting on him, will start to balance out the weight. So his speed will start to settle. So at the moment you can see that there's an increase in his velocity. 100 goes up to 9, goes up to 1,000, past 1,000, and eventually he should start to settle. Let's leave that for a second and watch. And now you can see the fastest free fall. It's stopped. He stopped increasing his speed. Now, this is a body that's flying through the air who should, in theory, be accelerating, but he's not. Because once you reach that terminal speed, that terminal velocity, the air resistance is balancing out. And you can watch this. This is on the presentation. You can see the whole thing, including how he lands, and he does survive, if that's what you're waiting for. We watched a video in class looking at whether a coin would kill you if it fell off the Empire State Building, and that's again another illustration of this air resistance. Now, why am I talking about this? Because there are consequences to velocity time graphs and projectile graphs, really, based on this air resistance. If we have a motion graph, if we draw a motion graph for an object which is suffering from air resistance, then we don't have this beautiful straight line, which is what we see when we have constant acceleration, right? So here we can see that this object is increasing its velocity, increasing its velocity, increasing its velocity constantly. So the slope is constant, and it should be equivalent to 9.81 if it's falling through the air. This object here starts off, note that the slope is the same at the beginning, but what's happening is that the acceleration is going to 0, which means that the slope is being reduced. And eventually the slope ends up flat because the acceleration is eventually 0. So there's two ways of interpreting this terminal speed graph. Firstly, as the slope decreasing to 0, or just the velocity increasing and then just staying constant, right? Both of those are important filters to look through this motion with. Understanding the slope aspect, understanding acceleration, and understanding what's happening to the velocity. What does an oblique projectile, or in fact any projectile, look like with air resistance? Well, we have the similar sort of thing. Remember, air resistance will affect velocity vertically, but it will also affect it horizontally. So horizontally, as the ball is moving up, the air resistance will try and slow it down. Basically, it's not going to go up as high as it should because the air resistance is slowing it down. So its maximum velocity will be less, right? In addition, horizontally, because we no longer have a situation where the velocity is constant, right? Acceleration is now no longer equal to 0 horizontally because we have this force slowing down the object. So what we have in this direction is a deceleration, and the object does not go so far right before it touches the floor. So this is the curve for an object which is decelerating. Okay, so no activity. I just wanted you to consider these two situations, take some notes, which would be very helpful. But that is today's lesson.